Okay, today we're going to do a lesson on vectors and parametric equations. Now, as you see up here, I have a group of vectors, and you'll notice something interesting about them. No matter where they're placed, if I took one and put it above another, you'd see that they're parallel. Something we know from algebra: when two straight lines are parallel, they have the same slope. So we're going to make a connection here with vectors and the vectored ordered pair. But first of all, let's just see how we get this. If we have an ordered pair at the beginning of a vector, which would be right here, that ordered pair is going to be right 3, up 1, 2, 3, 4, 5, 6, 7. 3, 7. Then we'll find that this ordered pair at the end of the vector, and remember these are directed vectors, that's why we have the arrows. We would go right 1, 2, 3, 4, 5, 6, 7, and up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Let's check those to be sure we're right. First one is right 3, up 1, 2, 3, 4, 5, 6, 7. The second one is right 3, 4, 5, 6, 7, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, the connection we've made in the past that you probably remember, when you have a vector, its two components, if this vector is a resultant vector, its two components are the horizontal here and the vertical here, which we see we can actually count and see that this is 1, 2, 3, 4, and this one is 1, 2, 3. Now, if you remember correctly from algebra, that was called rise over run when we found the slope, wasn't it? Determines the slant of that line, or the slope of that line. Well, it also determines the vector's direction. If you continue in the same direction, you're going to have the same slope repeated over and over. But first of all, let's do this. So in other words, let's do this, and we usually call the slope m. We notice that the slope here is going to be rise over run. Rise over run. Now notice also, remember how we got it before in algebra, we subtracted in reverse. We don't have to subtract in reverse, we could subtract either way to get the slope. But when you're doing a direction vector, you subtract in reverse because this is used for continuing the direction that it's already going. So if we take 10 minus 7, we get the 3. And if we take 7 minus 3, we get the 4. So there's two ways to come up with slope. Now, what a lot of people don't realize, also, let's take a look at this. The angle at which it's going from a horizontal also has a relationship to the 3 and 4. Now, think a second or a few minutes. If you've been in this class for long enough time, you're going to realize something. Which trig function is that? Well, this is my reference angle where I drew the arc. Rise over run is the same as opposite over adjacent. And we all know what that is from SOHCAHTOA. So this equals tangent. So this is a real important concept of seeing and tying things together here. We've got slope, tangent, and the component vectors of a resultant, horizontal and vertical, are all the same thing. And the other thing you'll see here is we've got a right triangle. So you can always find this hypotenuse, which is the resultant vector. Always find it by using the Pythagorean theorem, which is a squared plus b squared equals c squared, or you could say x squared plus y squared equals r squared. When you're dealing with trigonometry, we use that sometimes. Now, here's what I want you to see from this. This 3 and 4 that we have found by looking at this run and rise here occurs again and again on all these vectors that I have drawn up here. So if we wanted to write with these ordered pairs, which we have 3, 7 and 7, 10. If we wanted to write the vector equation, and this is considered, we'll just call this AB, and it's directed, then we would need the direction vector. Well, we've already found that. Remember we found the vector on the origin, which was also called the direction vector. It's also called the unit vector, is the one that you get when, remember, we subtracted in reverse. And that's what we just did here. So to write a excuse me, vector equation, you're going to notice that when I write it here, what it looks like, it's x comma y equals your first ordered pair at the beginning, which is 3, 7, and then I'm going to move this one over here for a second. We'll move him. We'll move you down here, buddy. Now, this will equal, or I'm sorry, 3, 7, because that is the initial point of our vector, plus t, which is the perimeter. It's called the perimeter, and this stands for time. And in a second, we're also going to write the parametric equation from this. But you'll notice we write this time the ordered pair. This is the direction vector, like this, because it represents the vector at the origin. And I bet you can guess that ordered pair pretty easily, because it's 7 minus 3, comma 10 minus 7. 7 minus 3 is 4. See, our x value is 4, our y value is 3 if you're talking about horizontal, vertical. And that's how we get our vector equation. And you'll notice here, I'll write it over here, we'll put V for vector here. Our vector equation is by taking those ordered pairs, subtracting backwards, finding your direction vector that goes here. T stands for time. 3, 7 is the initial point, the beginning of the where the vector starts from where we're talking about it. Now, that's done the same way every time, but I want you to notice something here. You see, the relative positions of airplanes are dependent upon their velocities at a given moment in time and their starting positions. Vector equations and equations known as parametric equations allow us to model that movement. So what I want you to see here is, let's just do this. Let's move this one vector right here. We'll move him down here. Now let's move another one to the end of that. And then let's move another one that we know that is equal to it to the end of that. Now these are not exact because I'm dealing with a smart board here, and it's not always in perfect alignment because of may need calibrations. Even when I calibrate it, doesn't always do it exactly. But what you need to notice is what this says is, well, actually I can't do it there now that I think about it. Not for this parametric equation. We'll erase this in a second so you can see how this is done with it, but I'll explain it over here where I've put these vectors together. But basically, this is a vector. Let's write its, or show how this works. See, let's just say this is traveling, happening every second. That's our t. Well, if our t is every second, then what it is saying is every second it's going right. Whoops, I don't want to do that. Excuse me. Every second it's going right 4 up 3. Then the next second it's going right 4 up 3. Then the next second it's going right 4 up 3. And so on. And you see how that determines the flight path. So if we can calculate that at in a constant direction, a constant speed here, making a straight line, it's saying, for example, and it won't be seconds necessarily. It could be done in kilometers per hour, miles, whatever. But our time right now, we're just doing this as an example. So every second, it's going right 4 up 3, right 4 up 3, right 4 up 3, which is causing this flight path. And therefore, if it's a constant, we can predict it. Its velocity and its direction is consistent. Now, if I was doing it for this one, of course, for this particular vector equation, we'd have to do it by putting our vectors, have to start with the one we have up here in the triangle, this one right here, and then it would continue to do the same thing, right 4 up 3, and right 4 up 3. There you would be able to see it, even though it's a little messy here. Right 4 up 3. You see that one, and of course the next one is above it, but it would also be right 4 up 3. And this is how we get the t right here is a multiple. If you notice, it's saying every second we're going right 4 up 3. And this is a picture of saying where we started, 3, 7, and every second we're going right 4 up 3. Now, I'm saying t equals a second just for the, it's just an arbitrary number of time right now, just so you can understand how vectors work in flight paths of planes and jets, and how it's related, and in a sense what it's used for. So that's kind of initially your introduction to it. Now, let's actually take another problem. You do not have to draw this every time it happens, but what we're going to do is we're going to take 2 ordered pairs that represent a vector, and we're going to write the vector equation. Then we're going to write the parametric equation. Let's see here. Let's go back to plane. Guess I'll have to do this in a little different way. Let's do new. Here we go. Now, let's say we're given this. Points A and B. Let's say A is 3, 4, and B 5, 5. All right. Now, what I want you to write, we want the vector equation, the parametric, and we're also going to write the Cartesian. Which a lot of the students don't know what that is, but it is the one they work with, or have been working with the most in algebra. It's the equation of a line. Now, let's do the vector equation first. We explained earlier. The vector equation looks like this, where x is the beginning, x comma 0 is the initial point, that's why it says 0 there, plus t, and then over here we have a comma b, which represents, as you can see here by this notation, this represents the vector equation at the origin. In other words, that 3, 4 we found in that last problem, or last explanation we went through. So, this is above us here is, we're talking about vector AB. Well, this is our initial point, or starting point, 3, 4. So this is not too difficult. So the first thing we do is put 3, 4 in here, and you'll notice these are with parentheses for an ordered pair point. This is not a vector representative. This is the beginning of the ordered, or the vector. This is the ordered pair at the beginning, plus t, which is our variable. And remember how we find the vector at the origin. We subtract in reverse. Since the vector is going from A to B, take 5 minus 3, which is 2. And we take 5 minus 4 for the y's, which is 1. Now remember, the 3, 4, I'm sorry, was it 4, 3? It may have been 4, 3. I think it was 4, 3, but it was the x, y was the run or horizontal. The x is the run or the horizontal. The y is the vertical or the run. So in this case, we're going right 2, up 1, every unit of this time. We're starting at 3, 4, going right 2, up 1, every unit of this time. Could be every second, every minute, who knows? Whatever the problem indicates or whatever the situation you're in. But this is how we write the vector equation. Now the parametric equation is writing an equation in terms of t. T is the parameter. This is very simple. All right, first of all, let's just say we've got our vector equation right here. This is our vector. Now if I want to write the parametric equation, very simple. We start with the x here. X equals the x in this ordered pair, the initial ordered pair, 3 plus, we have a plus, t times the x in the vector ordered pair. So that would be plus 2t. So there's the first part of our parametric equation. Then we have y equals the y value 4 plus t times the y. 1 times t is t. And this is our parametric equation. Now, that's pretty straightforward, pretty simple. So we've done our 2 here at the top. Now we want to write it as a Cartesian. That means in terms of x and y. So we have to get rid of the t's here. Well, now we're going to use some algebra. Simultaneous equations, and we want to eliminate the x and y's. So we're going to manipulate one of our equations and solve it for t. And then we're going to substitute. Let's see here. So we can get rid of the t. So let's take this equation and solve it for t. So we're going to transpose the 4, and we will have y minus 4 equals t. Now, the reason we did that, once you've solved for a variable, we can substitute this in for t in the other equation, therefore eliminating the t's so that we have only x and y's. So let's plug that in, and we would have x equals 3 plus 2 parentheses y minus 4. Now when you look at this equation, you can see this one right here. We have nothing but x and y's now. The t's are gone. T's represent the parametric equation. even though it's in the vector equation, the first one, its main component is the vector ordered pair at the origin that we have at the end of it. So now let's go ahead and do this. Let's get this in a form that we're used to in algebra, that's standard form. We would have, let's see here, distribute, and we would have 2y minus 8. And I teach my students, once they get out of Algebra 1 into Algebra 2 and beyond, to learn how to transpose, which just means move a term from one side to the other and change it to its opposite. So since we like the form ax plus by equals c usually, let's move our 2y over to the other side, and it becomes negative, and we have x minus 2y. Now we combine 3 and negative 8, and we get negative 5. So now we have our Cartesian equation. So this is our Cartesian equation. I know it's down here by itself, but we'll write it down here. This is the Cartesian. Okay. Now this all had to do with this beginning vector AB showing where it starts and where it, the direction it is going through 5, 5. It's a vector that is starting at 3, 4 and headed in the direction of 5, 5, going through 5, 5. That's why it's important to recognize direction, since we're dealing with that here. All right. Now I want you to try one on your own. So I'm going to write it up here, and then you can pause and write that equation for yourself, and we'll see how you do here. Let's erase this. Okay, I'm going to give you the two order pairs for A and B. We have A is 1, 4, B 4, 6. So we're given this vector, AB, that begins at 1, 4, and is traveling towards and through 4, 6. This is an object moving at a constant velocity through these points. It's starting at A and moving at a constant velocity. And see, that's why we were saying earlier, when you find the slope, or the horizontal vertical components, what you're finding is the constant velocity is the time moving through that 4, 3, or the 1, 2, 1, 2, 1 that we had in the last one. The run and the rise every second, or however fast it's going. So here's what I want you to do. Find your vector equation. Okay, let's make that look a little better. Find your vector equation. Find your parametric. And then find your Cartesian. So if you want to do that without seeing me do it, you're going to have to pause your video for a second, or for how much time it takes. Work this out, and then start it back up again, and you'll get to see if you have the right answer. Okay, if you're back, let's write the vector equation. The vector equation is going to be our initial starting point. But remember, this is an equation, so it must be written like this with an equal sign. Is 1, 4, so that goes here, plus t times the vector represented at the origin, which means we have to subtract backwards, b minus a. So we have 4 minus 1 for the x is 3. Then we have 6 minus 4, and we have 2. And there's your vector equation. Now remember, our parametric is going to be the x equals the x here, 1, plus t times the x in this vector ordered pair would be 3t. So we would have x equals 1 plus 3t for the first part. Then we do the y equals 4 plus t times 2. And we have our parametric equation. Pretty simple. Pretty straightforward. Now the next thing might take a little bit more math, because in this situation, looks like we're going to have to deal with some fractions in one form or another when we solve for t. So I'm going to choose this one again, right here, solve for t. So I'm going to transpose the 4. We have y minus 4. Remember, when you move it, the term becomes opposite. So that equals 2t. Then we have to divide by 2. So now we know that t is going to equal, let's do that a little better. Where are you? There you are. Sometimes I get in a little hurry. Had a little coffee this morning. All right. Now we can substitute again. That's what we want to do. We want to get rid of the t's. So we're going to take this, substitute it in for t. And the point is, for our Cartesian, we need just x and y and a constant. So we will have x equals 1 plus 3 times y minus 4 over 2. Now, there's a lot of different ways to work this. As long as your math's correct, it'll come out to the correct answer. So we have now, if I distribute the 3, looks like we're going to have 3y minus 12 over 2. Now, I always tell my students, if you want to get rid of fractions, multiply by the denominator, at least common denominator. Here we only have 2. Makes it simple. So next thing I would do, so we can get it in standard form, is multiplying everything by 2. So 2 on both sides, or 2 times x is 2x. 2 times 1 is 2. And we know when we take 2 times this particular fraction, it's just going to cancel these 2's and leave me plus 3y minus 12. Now we do some transposing and simplifying, and we have our Cartesian equation, which looks like will be 2x, transpose the 3y becomes negative, minus, and then we have 2 plus a negative 12, which is negative 10. Now we have the standard form, and this is our Cartesian form for this particular situation. So there's the Cartesian. Here, the parametric, and above that, we have the vector. There we go. Check that, see if you got it right, and then we're going to move on to another example. And we'll do that in a little bit, in part 2.